Now we're going to do some examples of operator theory. So let's do this example. So here's the question. So let H be a complex Hilbert space. And let X naught be an H. And then, so let be the inner product. Prove that T from H to C defined by T of X equals X naught is a linear operator. Find its norm. So let's do it. So what do we need to do to prove something's a linear operator? That's right then. For all alpha and beta, check with constants multiplying by vectors, they come out, right? So let's take a couple of complex numbers, and V and W and H. We have T of alpha V plus beta W equals, so it means take inner product of alpha V plus beta W with X naught. Now, how are we going to get those alpha and beta out of there? That's right, Peter. Just pull them out because of the properties of inner product. So that equals alpha V X naught plus beta W X naught equals alpha T of V plus beta T of W. Check. Excellent. And what about operator norm? So let's look at the norm of T of X, which would be the norm of the inner product of X with X naught. Well, that's just complex absolute value there. So how can we bound that? Yep, that's right, Lucas, Cauchy-Schwarz. This is less than or equal to this times this. And equality is achieved when this is exactly in the same direction as that. So this is a scalar multiple of this. So thus, the operator norm of T, which is the sup of Tx over x with x not equal to 0, and yeah, that should really be complex absolute value there, is it's not. Yep, so it really is a bounded operator. Cool stuff. All right, now let's look at a different one. So this is 5.1.2. Let T from L1 of 0 infinity to C be defined by Gf of S equals one over S times the integral from 0 to S of f of t dt. So question A is determine the kernel function. And then B, prove it's linear. And C, is it continuous? Is the operator T continuous? So let's answer these questions. So A, the kernel function is, remember we should be able to write Tf of S is the integral from 0 to 1 of K of St, f of T, dt, and somehow that has to equal 1 over S times integral from 0 to S of f of T dt. So therefore, K of S and T, what should go there? That's right, Peter. It's 1 over S times the characteristic function of 0 to S of T. Right. So in other words, this function's 1 between 0 and S and it's 0 otherwise. So that way your integral really is going 0 to 1. But yeah, good. All right, so now the next question is, prove T is linear. Well, it's just going to follow from the properties of the integral, because we put an alpha f plus beta g. And then it comes out using properties of the integral. No problem. Check. Let's pretend we did that. Good. And then the next question, is it continuous? Well, all we need to do is check if it's bounded. So let's see if we can take the norm of this and bound it by the norm of f. Now remember, of course, this is just going to complex numbers, so this is the absolute value of Tf of S, complex absolute value, which is the absolute value of the integral from 0 to 1, 1 over S, integral from 0 to S of f of T dt. And can we bound this in some way by the integral of f? I don't think so. But what can we bound it by? Well, that's less than or equal to, I can pull the constant out, because S is between 0 and 1, 0 and infinity, I guess. Yeah, times the absolute value of the integral of 0 to S of f of T dt. And then that's less than or equal to 1 over S times the integral from 0 to S of f of T dt with absolute value is less than or equal to 1 over S times the integral from 0 to infinity of absolute value of f of T dt, which equals 1 over S times the L1 norm of f. But because of that 1 over S, we can't really bound it. So it's not bounded. But however, if we knew in advance that f was bounded, then we could actually do an estimate, and this integral is the average value of f, and that would be less than the bound on it. So that's an interesting thing to note. However, if f is instead in the continuous functions, from 0 to infinity and intersect bounded functions with the sup norm, then the TF of S in norm, which is again, that's the value of TF of S, equals, okay, I've got to put the 1 over S in there, and go from that to that, to T is less than or equal to 1 over S and 0 to S of the sup. And so that would be sup F. That's a value of T. But then that's just a constant. It's just equals to the sup. That's a value of F equals the infinity norm F. And so T is bounded as an operator from a set of all continuous bounded functions from 0 to infinity to C. With the sup norm. But actually, with the L1 norm, you could actually find a sequence of functions where this is 1, but this goes to infinity. So that's because you could have it go to infinity around 0, and then this would work. Yeah, interesting problem. And let's see, we also have another question. So this is 5.2.7. So we're going to consider C1 of 0, 1, which is the set of all continuously differentiable functions on 0, 1. And that, by the way, that means they have one-sided derivatives. And so question A is show that C1 of 0, 1 with the sup norm is a subspace of C of 0, 1, but is not closed. So let's answer this question. So if F and G are in C1 of 0, 1, and alpha and beta are in C, we have that we need to check if it's continuously differentiable. Alpha F plus beta G derivative. Well, from the formulas of the derivative, it's alpha F prime plus beta G prime, which is continuous, since F and G are. So alpha F plus beta G is in C1. Therefore, C1 is a subspace of C0. That's called C0 if it's just continuous. Good. All right. But why is it not closed? So what does that mean we need to show? That's right, then we should find a sequence of functions in here that converges to something in here, but with respect to the sup norm, but is not in there. That's right. So I think you just need to find something that's not differentiable that's converging to. So, for example, we need something to end up with something that's continuous but not differentiable. So maybe something going to the absolute value, or absolute value of x minus 1/2. So we could take a sequence of differentiable functions that converges to that. So there is a sequence of differentiable functions f sub n that converges to that. So that would be absolute 2 f of x equals absolute value of x minus 1/2, which is not differentiable. So how could you construct such functions? Well, as follows. So the same as the other guy, absolute value of x minus 1/2, except when you're within 1/2 minus 1 over n, 1/2 plus 1 over n. And then in that area, you could find a parabola that fits that. And then that matches slopes and points at endpoints. And so then, if you take the suit norm of fn minus f, that's going to be less than or equal to 1 over n, because this distance right here would be 1 over n. And so, therefore, fn converges to f, but f is not in C1. So therefore, this subspace is not a closed subspace. And the next question is interesting also, is why don't we look at a linear map defined by ddx. So it's going to be a map from C1, 0, 1, to C0, 0, 1. Show ddx is linear but unbounded. And so the proof is, well, what do I need to do? That's right, Peter. For all alpha, beta in C, and F and G in C1, we have that ddx applied to alpha F plus beta G by properties of the derivative. It's just alpha df dx plus beta dg dx. And this is continuous. So it's good. So therefore, ddx is linear. It's an operator. But now what about the unbounded part? That's an interesting question. Yeah, so we're looking at the sup norm. So can we make the derivatives go to infinity without the function going to infinity? Good idea, then. Right. We could do something like this. We could have f of fn of x is something like this, where it gets bigger and bigger. And this could be a 1/2. And then and then it just kind of goes like that or something. Yeah, so it's still continuously differentiable, but then it gets more like a steeper slope right there. So let's see, how could we do that? Oh, or we could just do it at the end. Very good. Yes. Good idea, Sharon. Right, just do x to the n. Right. Okay, that's a simpler example. Good. All right. Great. So, so note that fn of x defined by equals x to the n, right? This function is an example of a function that's continuously differentiable on the 0 and 1. But now let's look at ddx of fn of x. And so this would be n x to the n minus 1. And this approaches n as x approaches 1. So therefore, the infinity norm of fn is equal to n. So, and so this is, so even though, oh, sorry, ddx. But the infinity norm of fn itself is just 1. So therefore, the sup of ddx, so overall n and n, of ddx of fn over fn, but these are infinity norms, equals infinity. So therefore, ddx is unbounded. Good job, guys. Way to go. Interesting stuff.